You can represent a particle's motion through either waves or trajectories. And this is 1,000 different ways a particle can potentially go from point A to point B. But the path it always takes is this one. These two basic ideas led Erwin Schrödinger to discover an equation that would change the way we think about physics forever. So how did he do it? In 1926, Schrödinger published 6 papers at the rate of about 1 a month, where he essentially laid the foundations of an entirely new branch of physics, quantum mechanics. In the first of these 6 papers, the F equals ma equivalent of this new theory, Schrödinger's wave equation, made its first appearance. It is to this paper and the thought process that led to his initial discovery that we will turn our attention to. Schrödinger begins this groundbreaking paper with an equation known as the Hamilton-Jacobi Equation. Although it might look intimidating, I assure you there is an intuitive visual way to understand it. And the path we'll take to get there is to focus on this term, the action. To truly understand the role that action played for Schrödinger, we'll need to take a brief tour of its history. The action was originally defined in 1744 by the French mathematician Pierre-Louis Maupertuis. Motivated by a desire to unify optics and mechanics under a single principle, he defined the action of an object as the mass times the velocity times the distance traveled. Although it's admittedly quite an abstract concept, you can intuitively see that, all other things being equal, an object with more mass has more action, and similarly, an object that moves faster or farther has more action. So for any part of an object's motion, we can define its action. And to get the total action, we just need to add up all the parts, which in the continuous case turns into an integral. Maupertuis' brilliant insight was to conjecture that all objects obeyed what he called the principle of least action. Of all possible paths that an object can take, the one that it must always take is the one that minimizes the action. And just as the way to find the minimum of a function is to take its derivative and set it equal to 0, the same approach works for the action. To find the true path, we set the variation of the action to be 0. In the ensuing decade, this principle was further developed by Leonhard Euler and came to its near-complete mathematical development in 1788 with the work of Joseph-Louis Lagrange. In a 2-volume work titled Analytical Mechanics, Lagrange desired to turn Newton's vector-based physics into essentially an equivalent, pure mathematical theory that made no use of the concepts of vectors or forces. He was proud to claim that this work contained no diagrams whatsoever. Using the principle of least action as a fundamental guide, Lagrange's analytical approach to physics proved to be incredibly successful. He showed that one could simplify Maupertuis' principle by taking an object's potential energy, kinetic energy, and subtracting them. Then integrating this over whatever time span you happen to be considering. We thus have 2 entirely different yet equivalent ways of representing the action. One that involves an integral over distance, and the other an integral over time. Moreover, Lagrange showed that the principle of least action in this form leads to what is known as the Euler-Lagrange equations, which he wrote in terms of kinetic and potential energy. In fact, by solving these equations, one gets the exact same results as Newton's F equals ma approach. So Lagrange successfully turned solving physics problems from complicated free body diagrams into pure algebraic manipulation. It wouldn't be until William Rowan Hamilton appeared that we would get the Euler-Lagrange equations in the way that we know them today, written in terms of the Lagrangian. But Hamilton accomplished something much more for physics than just writing the principle of least action in terms of the Lagrangian. Not only did he put the final touches on Maupertuis' principle, Hamilton also further developed Maupertuis's initial desire to unite optics and mechanics. In 1833, Hamilton made one of the most important and arguably most underrated discoveries in all of physics. He realized that the motion of a particle in classical mechanics can be represented by a wave. That's right, before quantum mechanics ever came on the scene, Hamilton discovered a version of wave-particle duality. Or rather, to be more precise, he discovered a duality between particle trajectories and wave fronts. Not only that, he was able to show that both mechanics and optics contain this same type of duality under a single framework now known as Hamilton's optical-mechanical analogy. The analogy goes like this. Suppose you shine a beam of light. There are two ways we can describe this motion. First, with waves. After a certain amount of time has passed, say 1 second, the light will have traveled a fixed distance. We mark the outer edge here and refer to it as the light's wavefront. This wavefront consists of all the points of constant time, t equals 1 second. If we let another second pass, the light travels further and we mark a second wavefront, consisting of all the points the light travels to in 2 seconds. We could of course keep repeating this process, and also consider wavefronts for arbitrary time spans. The second way we can describe the light's motion is with rays. We imagine the light is composed of particles that follow along certain trajectories called rays. Now, between any 2 points A and B, the ray behaves according to Fermat's principle, which states that of all possible paths for a ray, the ray must always travel the one that would take the least amount of time. And by checking different points, we can see a direct consequence of this is that the light rays are necessarily orthogonal to the wavefronts. So Fermat's principle provides a link between waves and rays. It also leads to another fundamental equation of optics known as the iconal equation, which determines the wavefronts. So a beautiful duality emerges. If you first know the wavefronts, you can always deduce the ray trajectories. Similarly, if you know the rays first, you can deduce the wavefronts. Amazingly, according to Hamilton's optical mechanical analogy, particles in classical mechanics can be described in the exact same way. Let's now imagine just one classical particle that moves from point A to point B. The trajectory the particle takes here corresponds exactly to how a light ray travels. But what about the wave picture? What could possibly be the wavefront we use to describe this classical motion? It's none other than the action. Just as optical wavefronts were surfaces of constant time, we can formulate a wavefront that consists of surfaces of constant action. That is, all points that have the same value of action at a specific moment in time. So if the particle's motion to this point coincides with 1 unit of action, there will also be a whole range of points that the particle could have moved to that would have resulted in the same amount of action. And of course, we can repeat this process. Now, just as the true path of the light ray behaved according to Fermat's principle of least time, the true trajectory this classical particle takes is governed by the principle of least action. And similarly, the particle trajectories here are orthogonal to the action wavefronts. So the same type of duality as before emerges. By first knowing the action wavefronts, you can always deduce the particle trajectories, and vice versa. It is at this point we can get back to Schrödinger's original paper. Remember how Schrödinger began with the Hamilton-Jacobi equation? Well, this equation is what encodes the action wavefronts. It says that something called the Hamiltonian, written in terms of the position and the derivative of the action with respect to position, just equals the total energy. In our case, the Hamiltonian will just be the kinetic energy plus the potential energy. But the more general form of the Hamiltonian can also depend on time. In that case, the right-hand side of the equation becomes -1 times the partial derivative of the action with respect to time. So the Hamilton-Jacobi equation is essentially an equation of motion for the action. By solving it for s, we can find the action wavefronts. And of course, from these, also find the particle trajectories too. This is Schrödinger's starting point. The reason he starts here is because one of Schrödinger's main intellectual influences was Hamilton's optical mechanical analogy. It is an analogy he comes back to again and again throughout his famous 6 papers. In fact, not only was he influenced by it, Schrödinger desired to complete the analogy in a way that Hamilton never dreamed of. The next step Schrödinger takes is to make a change of variables. He defines a new function psi that satisfies the following relation, where k is just some unknown constant that needs to have the dimension of action. So if we plug this in for s, the Hamilton-Jacobi equation takes on the following form. Now remember, the Hamiltonian is just the kinetic energy plus potential energy. So written in terms of the momentum, it's this. In terms of the action, and then after our change of variables, it becomes this. Plugging it into the top equation, and then subtracting E results in the following. Now if we solve for psi here, we'd simply be solving the classical Hamilton-Jacobi equations in a new variable. So there wouldn't be any new physics to discover. Instead, Schrödinger decides to multiply by psi squared on both sides in order to then create a new variational problem, which he defines by taking the integral of this term over all of space. He labels this quantity J, and it's a functional, which is just a technical term for a mathematical object that takes a function as an input and outputs a number. This is the most critical juncture of the derivation, and where Schrödinger takes the incredible leap of insight that no one before him had ever taken. You see, though Hamilton proposed a beautiful framework that united optics and mechanics, it really only works in a certain limit. In optics, only when the wavelength is short does the ray description match the wave description. As soon as the wavelengths become comparable to the path length, the ray description entirely breaks down. Certain features that rays cannot possibly explain begin to occur, and only the wave picture remains. The regime where both the wave picture and ray picture agree is called geometric optics, and the much broader regime is referred to as wave optics or physical optics. In fact, by the early 1900s, Maxwell's equations were already used to show that a light wave must satisfy this wave equation. And the solutions to this equation have the following form, where A is a function describing the amplitude of the wave, N is the index of refraction, lambda is the wavelength, and L is a function called the iconal. After plugging this solution into the above wave equation, we get 2 different equations corresponding to the real and imaginary part. Focusing on the real part, we can see that if we take the limit as the wavelength approaches 0, we get the iconal equation, one of the fundamental equations of geometric optics we saw earlier. Remember, it is this equation that gives the wavefronts and consequently allows us to also find the light rays orthogonal to them. By the time of Schrödinger's paper, all of this was well known experimentally and theoretically. But on the mechanical side of Hamilton's analogy, things were different. Various new phenomena had been observed in recent years, like the surprising results of blackbody radiation, the photoelectric effect, and the discrete energy levels of hydrogen. Many prominent figures contributed to mathematical calculations that could account for some of these phenomena. However, physicists struggled to find a fully adequate way to explain things theoretically and had to impose seemingly artificial conditions to get predictions that matched experiments. The conditions that forced certain quantities like angular momentum and energy to take on discrete or quantized values came to be known as the quantum conditions. What Schrödinger sought to do was to find some deeper principle that would not just postulate these quantum conditions, but instead have them arise naturally as a consequence of it. Just like the integer values of a vibrating string naturally arise from the wave equation describing it. It is with all this in mind that Schrödinger wanted to find a similar wave equation for mechanics, one which could explain the recent experimental observations and at the same time reduce to Hamilton's description in a certain limit, just as the previous wave equation did for optics. It is this new variation problem he defines that does exactly that. As Schrödinger says in his paper, we seek a function which makes the integral stationary, and we replace the quantum conditions with this variational problem. In other words, setting the variation of J equal to 0 is the deeper principle that replaces the previous quantum conditions. And when he does this, he is essentially defining a new action with this quantity J. If you want to understand more deeply why, just pause the video here. So just as Fermat's principle of least time and Maupertuis's principle of least action required the variation to be 0, Schrödinger requires the variation of J to be 0. Carrying through the calculations, the first term here is just a boundary condition that Schrödinger deals with later in the paper. It equals 0. So we are only left with this term. And since the variation of psi can be anything, in order for the whole integral to be 0, the rest of the expression in here must be 0. Then letting k equal h bar, the reduced Planck constant, and moving e to the other side, we arrive at the time-independent Schrödinger equation, the fundamental equation of quantum mechanics. It is the equation that describes stationary quantum states. In other words, states that don't change over time. To illustrate just how promising his new equation was, Schrödinger continued on in the paper to solve this equation for the hydrogen atom. Amazingly, it results in energy levels that have to be discrete, in complete agreement with what was observed through experiment. The quantum conditions that others used as a starting point were not a postulate any longer. Rather, they arose naturally as a consequence of Schrödinger's approach, just like the vibrating string example. So Schrödinger was able to successfully do to mechanics what was previously done to optics. His incredible leap in this step is what turned psi into a continuous quantity over all space, completes Hamilton's optical mechanical analogy, and at the same time quantizes the system. In subsequent papers, Schrödinger would further elaborate on this new theory, provide alternative derivations of the wave equation, and eventually discover the right version of it that could also incorporate time evolution. Moreover, just as wave optics reduces to geometric optics in the limit that wavelengths go to 0, Schrödinger's wave equation reduces to the Hamilton-Jacobi equation as h bar goes to 0. A truly beautiful result. There's no better way I found to describe the importance of Schrödinger's work than a quote from the great mathematical physicist Freeman Dyson. The Schrödinger equation describes correctly everything we know about the behavior of atoms. It is the basis of all of chemistry and most of physics. If you're looking for even more ways to get intuition behind fundamental math and science concepts, be sure to check out brilliant.org. All their lessons in math, physics, and even computer science are filled with beautiful visuals that guide your intuition every step of the way. Not only that, each lesson also includes games, puzzles, and regular feedback to check your progress. So you'll always be learning by doing hands-on activities. If you'd like to try it out, you can begin learning for free on Brilliant by either going to brilliant.org/abidebyreason, scanning the QR code on screen, or clicking on the link in the description. Brilliant's also given my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant.